Experimental analysis of winglet effectiveness at low airspeeds. My name is Peter Schilling. I'm working with a couple other guys in the mechanical engineering department. We're advised by Jim Geiger, who's an adjunct in that department. So, winglets. This is a winglet. This is a particularly sexy kind of winglet called the split scimitar winglet. I think it's beautiful. I hope you do too. And this is currently available for a retrofit on Boeing 737s. And it increases fuel efficiency by about 6%. So that's what it's for. It is to increase fuel efficiency. That's the point. And I'm going to explain how it does that, why we're researching it, and some of what we found. So the point is we have an airplane. It needs to stay in the air, and it needs to move forward. So in order to do that, it needs to generate lift and overcome drag. And weight and thrust are things we don't really need to talk about because you have to overcome them. The thrust has to overcome the drag no matter what, and the lift has to overcome the weight no matter what, or you can't fly forward or up. It's bad. The first thing we're going to talk about is lift. Now, a lot of you have probably heard in your, middle school science classes something about air going over a wing and like two molecules breaking off at the front and having to meet magically at the back end. And then one goes faster than the other and it generates low pressure and whatever. That's complete bull. That is not how an airplane flies at all. It does have to do with differing velocities over the bottom and the top of the wing, but this idea that somehow two air particles that separate magically have to come back together just doesn't fit with any kind of physical law, model, or anything. Like if you throw two rocks out of your hand, do they always hit each other? No. You can think about it that way, whatever. It's actually a little bit more complicated, but not too bad. So you can see here, this is just off Wikipedia. You can look it up if you want. So the air that hits the wing basically gets redirected on the bottom, and then when it comes over the top, it kind of gets squeezed by the column of air on top of it. So when you put your thumb over a hose, the water comes out faster. It's exactly the same principle. So it squeezes the air kind of over the top of the wing, and that generates higher velocity. And you've all probably heard of Bernoulli's principle. If you take two sheets of paper and blow between them, they come together because higher velocity generates lower pressure, higher pressure underneath, lower pressure on top, thing moves up. And that's how an airplane flies, which is not actually all that magical, although it might seem a little bit magical when you first think about it. So what do we care about that? The problem is that you have this high pressure underneath and this low pressure on top. And when you get to the end of the wing, things in an area of high pressure right next to something in an area of low pressure wants to move into the low pressure region. That's just, that's the law of everything. So what happens is that this air kind of comes and spills over the end of the wing, and it starts spinning out the back. And as the airplane moves forward, the spinning air kind of trails off the back in what are called wingtip vortices. And that actually generates drag. There are a couple ways to think about it. One is that you're putting a lot of energy into the air because you're making it have to move so much. And that energy has to come from somewhere. You can't just make it. And you can't really get it back because it's way out behind the plane. So what happens is that the engine of the aircraft has to generate all this extra energy to move all this air. And so that makes it less efficient. The other way to think about it, maybe a little more intuitive, is that the air coming around the ends just pushes down on the wing. And if you're trying to go up and something's pushing you down, you're not going to be as efficient. So parasite versus induced drag is kind of the trade-off we're thinking about. Parasite drag is just friction. So that's, you move your hand through the air, you feel air pushing on your hand. That is parasite drag. Induced drag are these wingtip vortices. You cannot generate lift without having wingtip vortices. You cannot generate lift without drag, and it's a really big deal. So, what do winglets do? Winglets, it seems pretty obvious now that you know the mechanism, is they just block that air from coming over the top. So the air has to travel farther, and it has this barrier between the high pressure and low pressure zone, and that will decrease the size of these vortices, thus decreasing the induced drag, thus making the aircraft more efficient. But that decreases the induced drag, but you're also sticking something big out into the airstream, which increases the parasite drag, and it also adds weight to the aircraft, both of which make it less efficient. So there's a trade-off here, and this is why you see some airplanes with winglets, some without. It really depends on their mission profile and what's going on. So this stuff actually happens. You can actually see in this picture, this is a Boeing C-17, and it drops a whole bunch of flares. If there's like a heat-seeking missile going at it, it'll drop all this hot stuff out below it to divert the missile. So all of this stuff goes straight down, but you can see that the wingtip vortices have whipped up this smoke into these kind of cyclone-looking things right here and right here. That's called a smoke angel. It's pretty cool. So winglets, we'll go back to those. This airplane has winglets, by the way. It's hard to tell in the picture. But even with winglets, you can see that these wingtip vortices are really big. So the history of winglets goes back to the dinosaurs, as you can see from this dinosaur descendant here. And if you look at this, I mean, that looks pretty familiar now that you've seen a picture of a winglet. I mean, that's really what a winglet is. Birds have been doing it for millions of years. And it wasn't until 1897 that someone actually looked at this and was like, whoa, oh, wow, this is how like birds fly and stuff. And this was known 1897. The first flight was in 1903. So people were thinking about winglets even before people were flying. So there was a guy named Lanchester. He was English, so he wasn't looking at bald eagles, but he took a lot of trips on boats and was looking at seabirds a lot, just kind of staring at them. And he came up with this idea in this patent in 1897. Was like, hey, you could actually put something on the end of the wing to make this more efficient. But most of the aerodynamic progress after that was mostly concerned with getting off the ground, first of all, and then just getting higher and faster, and not necessarily more efficient. Gas was cheap, everything was loud and smoky and wonderful, until 1970s when there was an OPEC oil embargo. And suddenly all these airlines couldn't afford their own jet fuel. So they were looking at ways to make things more efficient. A guy named Richard Whitcomb at NASA, amazing, brilliant guy. He had already invented two things that revolutionized airliners, a wing shape and a fuselage shape. And he thought, well, 3 is better than 2, so why don't I come up with another thing? So he spent 3 years in wind tunnels coming up with this stuff, and he eventually came up with this winglet design you see here. NASA and the Air Force tested it on this KC-135, and they found 20% decrease in induced drag, which is enormous. 20% decrease in drag makes you 20% more efficient. So, why not? This was flight tested in 1979. By 1985, every major airliner manufacturer had winglets. So for low-speed applications, we have to focus on because of BU's test equipment. Basically, that's limited to this kind of thing, which is a sailplane. This aircraft has no engine, gets towed up into the air, and rides the thermals as far as they can go. They do big competitions. They're very intense. They're decided by very thin margins. So Mogmer at Penn came up with this design. He spent 11 years, as you can see, coming up with this very optimized winglet design for low airspeeds. So, like I said, efficiency is important. Okay, $32 billion of fuel last year, 17 billion gallons of jet fuel. So 1% increase is 170 million fewer gallons of jet fuel being burnt. That is 1% less carbon emission, and it's all around just a good thing. So the project that I did was motivated by, we're looking at all these different winglets, all these different airplanes have them, some don't. The performance data are very, very, very well guarded by the aerospace industry. I worked at Boeing last summer. I have no idea what their performance metrics are. They only are released to people who absolutely need to know them. So we're trying to come up with a little bit of our own way to test this out to see whether or not winglets are really worth the hype. Because as you could see from the first image, they also look really cool, and that might be a selling point. So what do? BU has a wind tunnel. It's very small as wind tunnels go. Most major wind tunnels, like the one at MIT, is 10 feet across. Ours is 18 inches. So, you do what you can with what you got. And theirs goes up to, 400 or 500 miles an hour. Ours goes to, 100. So you do what you can. But a lot of people ask me, why do you use wind tunnels in the first place? Well, the idea is that it's not rocket science. It's airplane science. Okay, this is airplane science in a nutshell. This is how air moves. If you can solve all these equations for all these variables all at the same time, you could figure this all out and not need a wind tunnel ever again. We do not know how to do that. Mathematics has not progressed to the point where we are able to solve these equations. And so we go to the wind tunnel. What do we do? So we 3D printed at BU, and we also outsourced some of it, these test articles, a base airfoil, and a airfoil, a couple different winglet designs. And we stuck them in the wind tunnel, and we ran it all up, and we got all this data, and it came out, and it looked absolutely terrible. And we were like, well, what's going on? And a little investigation turned out that nobody had really validated the test procedures that would come into the wind tunnel in the last 10 years. No one had gone in and looked to see if what we were doing was correct. So we spent 30 hours one weekend just in there, just trying to figure this out and trace back all these things and whatever, and it was a mess, and I've got a lot of recommendations for the department. But the point is that we can predict through some simplified forms of these equations what was going to happen. So we had 3 different winglet designs. We had blended up, which is just like this, blended down, and then the fence kind, which is this one. And so our prediction was that the fence would actually do better. What you're seeing here is lift versus angle of attack, which is the angle at which the airplane is tilted relative to the air. So we're saying, higher angle, more lift per angle is good. And what we found was not quite what we predicted. We found, so this is our base airfoil right here. We found all our winglet designs to actually slightly increase the performance, which is cool. Now, what we're really looking at, though, is the ratio of lift to drag. I talked about induced drag. You can't have lift without drag. So you want to generate as much lift as possible with the least drag. Makes sense, right? So this is lift to drag ratio on this axis and lift on the x-axis. And you see that this is our fence winglet. Actually outperforms all the others by a significant margin. And this is the same thing, but with airspeed. So we've got 0 to 50 meters per second. That's 0 to 112 miles an hour. And we see that the base airfoil does what the base airfoil should do. The fence winglet actually does pretty well. And the blended winglets, that peak and there, whatever, we have no idea why that's there. That should not be there. That should not look like that at all. Visor has no idea. No one has any idea. So that's what it looks like. But the punchline is statistical significance. All these measurement variables, all the instrumentation has errors associated with it. All the math that we do has errors associated with it. You have to gather all of those errors together and see whether what you're measuring is actually what's happening. So when we did that together, we haven't done that yet. So you can come on Friday, April 29th from 10 a.m. to 10:30 a.m. in Photonics 203 and see the full half-hour presentation of this report at the College of Engineering with my 2 colleagues and our advisor, and you can learn whether or not we actually found anything worth talking about. So, thank you. Got a very limited time, but I could take a couple questions. Any questions? Sure.
What are the next steps for this project?
The next steps for this project, as I said, are advising the Mechanical Engineering Lab Committee on proper procedures for this kind of experiment. When they got rid of the aerospace department, everybody who knew how to do this stuff left. They didn't leave any paper trail. We're all trying to figure it out again. So that's really the next step. Our research itself doesn't really have any practical application, but that's really what we found out. Any others? All right, thank you.